Здравствуйте.
Hello.
Hello.
Alexander Markovich, don't you mind to start? To be the first speaker?
Thank you.
So
This
it's,
will be my privilege.
yeah, it's 1 o'clock. Let us start the seminar in memory of Professor Омельянчук, Alexander Nikolaevich Омельянчук. I think that I will not make any specific introduction because all the speakers will tell their experience about their works related to Professor Омельянчук's papers, work, collaborative work, etc. So let us start from Professor Zagoskin.
Will I be able to share my screen?
Ah, sorry, I didn't allow yet. Yes, please.
Thank you very much. So, just a second, I will pull up the. As usual. Yeah, here we are. Okay. Just a second. This all, excuse me. Excuse me, just a moment. It takes a little. Okay. Yeah. So, can you see my screen?
Not yet.
Interesting. Okay, can you see it now?
No.
I really hate this technology. Well, it lets you down. Okay, can you see it now?
Yes, now yes.
Yeah, great. Thank you very much. So this is, of course, a sad occasion. I wish Alexander Nikolaevich was with us years from now so that we could take advantage of his friendship and his knowledge and his mentorship. But I had this great privilege of graduating from Kharkov State University. And while I was still studying there, Professor Janssen brought me in touch with his friend and colleague, Professor Kulik. Both of them, unfortunately, are no longer with us either. And then already I made my acquaintance with Alexander Nikolaevich Омельянчук. And after university, I went to work at Division 20, the theory division headed by Igor Arestовich Kulik. And Alexander Nikolaevich was my supervisor with Kulik, and more than that, he became indeed my teacher, friend, and mentor. At that time, at 15th in particular, you could just walk along the corridor and be sure that you will find people who will answer any of your questions concerning physics and answer these questions at really the world level. So you probably don't know that, but Alexander Nikolaevich played a very important role on the early stages of D-Wave systems. I invited him to collaborate, and he helped us to survive and develop through the early stages of this. And some of people present here who were also involved, like Professor Michov, will tell you more about this. But interestingly, what we are doing now is also related to work done in particular by Alexander Nikolaevich at those early times. So I would like to say a few words about the problems which we have now and which directly stem from those early days. That is, we do have now the capacity of producing really large quantum devices from the early D-Wave processors containing about 100 quantum bits. Now the numbers, excuse me? Can you hear me?
I'll try to switch off those who forgot to switch off their microphones.
Yes, so right now the numbers of quantum bits in the structures, well, are counted in thousands. And the problem is that now you cannot simulate these big structures classically, and we do not have quantum computers yet which could do it in a quantum way. So this means that we need to develop some better means of doing this. And so we planned to go the way, say, hydrodynamics and aerodynamics went in its days when there was no access to quantum, to large classical computers, and you could not numerically solve any realistic equation. That is going through search for some dimensionless parameters which can characterize qualitatively different regimes of their operation. There is a way, well, there is only limited number of such parameters, even though it is still too big to go through manually. And there are some theoretical reasons to believe that such reduced description is possible. There are theorems which limit the space inside the Hilbert space, which can be accessed by any quantum systems in its generic evolution. There are quantum speed limits theorems, and there are also some results showing that you can get qualitatively different regimes, like different chaotic and hyperchaotic regimes in quantum systems. And for example, the number of positive Lyapunov exponents which control these regimes only grows linearly with the number of qubits in the system. And this is something which gives us reasonable hope that such kind of parameters can be found for a generic quantum system. One example of such parameter which we obtained recently using the random walk model of generic quantum evolution actually is pretty simple. It only is controlled by the interqubit coupling, number of qubits, and time of evolution and the coherence time. And when we applied this parameter to quantum behavior of D-Wave processors, which was quite controversial because there was no conclusive evidence either for or against their purely quantum operation. In earlier days, we found that they're well inside the quantum domain. So this is something which I think is important for the general development of quantum technologies, and it is related directly to some of the work that Professor Омельянчук did, say, early in this century when collaborating with us. And now just a bit of a teaser related to another part of what he did, and that probably is the most celebrated and most important part of his results. That is his development with Kulik and with Robert Schechter of so-called point contact spectroscopy, where they explained results by Professor Janssen's groups and made some interesting prediction. So what is the thing we are doing now? We want to get the full set of quantum analogs to circuit elements. You know that there are pretty trivial analogs to reactive circuit elements. Quantum inductance, for example, small enough Josephson junction, which satisfies certain criteria, can be considered as a nonlinear inductance, which can be in two states at once, realizing quantum behavior. Same applies to quantum capacitance. The circuit is a little more complex, but the principle is the same. The question is, can we do the same thing with active circuit elements? Well, it may seem self-contradictory because active element, well, should have dissipation, and dissipation would kill quantum coherence. Fortunately, this is not quite the same, quite so. And this, well, anyone who worked at the Institute for Low Temperature Physics would immediately recognize this picture. This is the principle of point contact spectroscopy, developed, as I said, by Alexander Nikolaevich and his colleagues. The idea is simple. If you have a ballistic regime, when your electrons fly through your sample, and then the conductance of the structure will be determined by its nearest part, in this case, the orifice in this model. So this is a realization of, in classical physics, would be called Knudsen regime, and what was developed by Landauer. Well, this is a particular and specific implementation of this. And the electron distribution function would be dragged along these trajectories. So only the electrons which come from that infinity will have this kind of Fermi energy. All the rest will have this Fermi energy. So you create this fine, funny distribution function with the dip, or it will have a peak instead on this side of the orifice, which can be used to probe the phonon spectrum, because clearly the transitions with these frequencies will be privileged. And indeed, you can, and indeed, you can use this, and it was used very successfully, to probe the phonon spectrum of metals. But the point relevant to our research is that here, the region where conductance, the active criterion, active parameter of our system is formed, is separate from the origins at infinity where all the dissipation happens. So we have two different time scales. And on the one of these time scales, you can have quantum superposition of states with different size of the surface, so to speak. And so you will have a quantum analog to resistance. And of course, you can have a quantum analog to memristor as well. And this is something which we consider quite interesting and promising. But this all, to a very large degree, is due to what I learned from Professor Омельянчуka. And his work will continue, I would say. It is really tragic that he left us, but as I said, his legacy will be with us for years to come. And thank you very much for inviting me to this event. Thank you.
Thank you, Alexander Markovich. And if you do not mind being in the format of seminar, I'd invite listeners to ask to ask questions or maybe add comments. And if it is not the case, let us continue. Thanks a lot. Professor Van Rutenbeek, please.
Yes, thank you very much. I'm here. I've started sharing my screen. I hope you can see it.
Yes, we do.
Okay, thank you. So first, let me say that, of course, we greatly regret the loss of the great man and great scientist that Alexander Nikolaevich Омельянчука was. And we also mourn, of course, the loss of many lives in the war that's currently raging in the Ukraine. And everybody here is very much with all of our good friends and colleagues in Ukraine, and hoping that soonly this terrible fighting will stop. I have put up a picture here that was taken during a visit, my second visit to Ukraine in 1996. And you see here, of course, you will recognize Sasha Омельянчук, and next to him is my wife. I'm the one taking the picture. You will also recognize Yuri Kolesnichenko. And this was one of the many occasions of great warm hospitality that we have encountered. The connection, and this is what I wanted to use this time to remind you of, the connection between Kharkov and Leiden is going back to a man that you will all know, Professor Shubnikov, because Shubnikov has been visiting Leiden in the late 1920s, early 1930s, working together with De Haas, where he has done wonderful work. And after returning to Kharkov, implemented a lot of the low temperature techniques that he had also learned in Leiden. Now, at the end of the Soviet era, when it became possible again to mention the name of Shubnikov, who, of course, unfortunately was killed by Stalin. And so when the name of Shubnikov could be remembered again, several of the colleagues at Kharkov took the initiative to assemble a book in memory of this great man. And they came to visit us. Specifically, this was Peter Schumacher, who came to visit us in Leiden, offered the book, and proposed to re-establish the connection between Kharkov and Leiden. On this initiative, my colleague Reija Jochemsen and myself, the next year, paid a first visit. That was then 1991 to Kharkov, where we had a full week of exchange of scientific progress, of lots of socializing, and we've met an enormous number of very talented colleagues that which would form the start of a collaboration that we've had over many years. More recently, it's been less active. Many people retired or moved to other fields. But this event, this visit, and the ensuing collaboration has had an enormous impact in science in Leiden, and especially the science in my group. So this is another picture which was taken then in 1993 when we had both Professor Omельянчуka and Professor Jansson, who you see here. So I have the honor of being in between Professor Jansson and his wife. Here's the young Yuri Jansson. Yuri Jansson, in the meantime, obtained his PhD in Leiden and is now making a successful career at Shell. There is the son, Alex Jansson, who is not in the picture, who also obtained his PhD in Leiden and is now working at ASML. They are all doing very, very well, and so this is a continuation, let's say, of the very successful scientific and intellectual tradition from Kharkov, which is still very much alive. So I'm showing you pictures of happier times. Here is a one where we are visiting the tulip exhibition near Leiden. So there were many opportunities to have input and learn from both the experimental work in Professor Jansson's group, as from the theoretical work in Professor Omельянчук's group, which have guided us in thinking about atomic contacts. So contacts smaller than what Professor Jansson had been working on, but they fitted exactly the theoretical concepts that Professor Omельянчуka had developed. And moreover, it turned out to be possible to use superconductivity over atomic contacts in order to have an exact representation of conductance channels, which you could extract from experiment. And this was only possible thanks to the work that Professor Omельянчуka had started and has later been taken up by many. And this is, has guided us through the years over many of our experiments, and is still very much having a great impact on all the work that we are doing today. With that, and a few impressions of these happy earlier days, I would like to thank you for your attention. I would like to express my condolences to everybody who's been very close to Professor Омельянчук. And I wish you all strength in these very difficult times. Thank you very much.
Thank you, Jan, very much for the nice collection of pictures and memories. And thank you for the wishes in the address of Ukraine. Thanks a lot.
Pleasure.
Now I'd like to announce the talk of Boris Ivlev, please. Are you here, Boris? Is Professor Ivlev here with us? Maybe later. Then Dr. Olsner, please. Gregor, can you connect?
Thank you, Sergey. Can you hear me?
Yeah. Oh, yes, yes.
Let me
Can
share my screen as well. So can you see my presentation?
Now, yes.
So maybe I start with a short encounter which we had while Professor Омельянчук was visiting us, I guess, for the second time. Must have been around 2012 or 2013. Actually, the second time while I was already at the institute. And one day he didn't come to the institute, and we were, Pascal and me, a colleague of mine, we were somehow worried, and we went to the guest house just to see if everything's fine. And actually, was everything fine? I think he was just not feeling well to go to work to this day. But he wouldn't let us leave before we had a coffee together on his balcony, which was funny because the guest house was very small, or is actually very small. And I remember that I don't know what we spoke about, but we were sitting for quite a time on his balcony just drinking coffee, which he prepared in some small cup. I guess it was really great hospitality, although he was not at home, I have to say. So let me shortly discuss in my presentation how we actually work together. And I should use this keyboard. Now, so we did some first experiments on superconducting quantum bits coupled to resonators which were at high frequencies around 2009. And what this does is actually, compared to the work which has been earlier performed at our institute, that it enables also resonant interactions of these two subsystems. And the first theoretical analysis actually was carried out by Professor Омельянчук. And a lot of further work which came afterwards was actually based on this first encounter. So the idea was we have these coplanar waveguide resonators which are formed just by superconducting films interrupted at 2 points, this central conductor, and this gives you the resonance frequency. So the length of this guy is something like 3 centimeters, which approximately is a resonance frequency of 2.5 gigahertz. So you can get very high quality factors. Because the temperature, the frequency is at 2.5 gigahertz, at 20 millikelvin, you have very small thermal propagation. The second system, which we considered, is a flux qubit, which is tunable by external magnetic field, so that you can describe it by such an Hamiltonian, where you have this bias, which you apply by external magnetic field, and you have this tunneling amplitude, which gives you in total such an energy level splitting with a minimal level splitting delta, and then splitting actually linear to the external flux far away from this degeneracy point. And what we did is actually we prepared a sample. I was calculating the first design. We put 4 qubits just to be sure that one of them would have a coupling which is high enough to the resonator. So I simulated the energy level splitting, and we found a good parameter set for the junction sizes so that you can get 2.5 gigahertz splitting at the degeneracy point and persisting current of 135 nanoamps. And then we just put it to the fridge, and that was actually some of my first experiments doing it 20 millikelvin. So what we simply did is we used the current source to apply a magnetic field, sweep the magnetic field, and then we had a vector network analyzer with some advanced setup to characterize the resonance frequency of this oscillator. And then you have to amplify the signal again. And then just measure transmission also with maybe an additional microwave source. And this is actually what we measured in the first, actually the first sweep of current through the qubits. And what you can see is these are the qubits which are actually estimated to look like this. So you get a very small dispersive shift, a small shift in resonance frequency when you hit the degeneracy point. But what more impressively is this very large spike, which we can zoom in maybe. So you can see in amplitude, for example, this is a drop of almost or more than 20 dB, and a large frequency shift of the qubits in phase being the black signal, and red being the transmission amplitude through the oscillator. And then what you immediately continue to do is you sweep the bias current, and you use an additional excitation frequency just to make a spectroscopy of the qubit to extract the minimal energy level splitting, which was in this case 1.8 gigahertz, and the critical current, the persistent current, I'm sorry. And then we measured this very nice picture here. And what you will see immediately is that these bias points correspond to resonant interaction points. And with these two pictures, we actually tried to write a publication and publish this, and actually was rejected in the first round. So in principle, what was missing there was some kind of theoretical analysis of this picture. And you can put together a Hamiltonian where you have the qubit, where you have the resonator and some interaction, and what is happening in these interaction points here, where the actually this is wrong, it should be, oh no, it's G1. In these interaction points, we actually get an avoided level crossing, which leads to this shift in energy levels, such that you don't probe the pure resonator state, but you probe the shifted resonance frequencies, such that you cannot get any signal at this point. And what you can see here is the nice fitting, which was done by Professor Omельянчуka. And after we put these two pictures into publications, was very quickly accepted actually at PRB, and this theory which he developed was then later used also to describe these interaction points in more detail, because you would usually expect that you see two peaks in a distance of G, actually 2G, which we didn't observe because in our case, the qubit decoherence rate was too high, such that you get actually a damped peak of the resonator here, which is hardly visible. And as I said, afterwards, we continued our work on single qubit interacting with cavities, and strongly, when we strongly drive it, we get such nice pictures where you get amplification or larger damping actually. And yeah, everything we could describe later with some effort in some theoretical way. And yeah, I'm very grateful that in this early time of my career, I met such great persons which could help me to understand what I'm actually doing. So that is all from my side. Thank you very much for inviting me. And I know it's very specific discussion here, but I hope it was anyway what you expected.
Thanks a lot. Thank you so much, Gregor.
So if there's any question, I'm happy to answer it as well.
Now or later, right?
Yeah, of course.
Questions or comments? Yeah, in my talk later on, I'll also tell about similar calculations.
I think it was a very fruitful cooperation. I hope we can continue now.
Exactly.
That our focus goes more in this direction again.
So we continue to find different sides of Professor Омельянчук's works. all of the talks were very different, and now I hope we'll continue with Professor Ilyichev. Evgeny, please,
Okay.
from the next room, right?
Can you see my screen now?
No, only you. And
Not yet.
Only me.
Like it's two rooms between us.
no interference, nice isolation. And now
So-
F5.
Now you see it, yes?
Yes, but not in the full
F5,
screen
okay.
mode. Now very nice.
Very nice. Okay, good. So, to memory of Sasha, unfortunately, he's not with us anymore, but yeah, life is life. And let me say following that we start our collaboration at the beginning of century, so more than 20 years ago. And as Sasha Zagoskin told you already, it was somehow basis was the Wave project. I was invited as experimentalist and Sasha somehow to join the theoretic group, which was organized in the Wave by Sasha Zagoskin. And and even after the Wave Pop project, we continue to collaborate, to work together. And I must say that our first paper was published already in 2001. And it was somehow pure classical, if you want, about current phase relation in Josephson junction. In those times, we had an idea, maybe try to make qubits by making use high TC superconductivity. Later on, our opinion was changed a little bit, but nevertheless, we attempt to do it in frame of this project. And you see, totally we have published 15 papers together and one monograph about qubits. And probably it was the first book which was written in Russian language about qubits. And we met and worked together in many places, of course in Kharkiv and Jena, but then we were working together in Tokyo, where in Frank and Ori group, we spent several months there. And of course in Vancouver with D-Wave, with people from, I believe that Toля Smirnov is here, maybe he can hear me. He is still working with D-Wave. And yeah, it was very nice and productive time. And by the way, our work was awarded by Verkin Prize of National Academy of Science of Ukraine in 2017. And also I'm proud we got this prize together with Sasha and Sergei Shevchenko, who is now organizing this meeting. And I would like to say my words of support because, I mean, you see in Kharkiv now is terrible situation and Sergei has power and forces to organize such kind of meeting, which is really, I wish you really to be strong and I mean to be strong and just, yeah, in this terrible time, I mean, it's no words, of course. I express my support to Ukrainian scientists. And our question, so let me go a little bit to science. And you know that Sasha is pure theoretician, I am experimentalist. And at the beginning of our activity, I always ask a question. If you have some kind of macroscopic structure like Josephson junction or whatever, how to distinguish experimentally between classical nonlinear dynamics and really quantum physics, quantum mechanics? Because if you will ask this trivial question just for oscillators, so by making use spectroscopy is difficult to do it, how you will do it somehow? Is there some kind of recipe how to distinguish in between these two regimes, because they are definitely different? And of course, question was not quite general. We are from experimental physics. We have our qubits. This is just example of flux qubit, which we form and we fabricate in Jena at the PhD. You see, this is construction of flux qubit, which proposed by Hans Moy around 2000, yeah, at the end of the last century, 99, something like this. And point is that this structure consists of 3 Josephson junctions, and we know from textbooks that Josephson junction is just non-linear classical oscillator, can be at least expressed in frame of RSG model and whatever. And point is, we have measurements set up like this. We couple it, by the way, it's very close to circuit QED. We couple such kind of structure with tank circuit with resonance frequency, and all parameters are shown here. And point is, by measuring this impedance, is it possible somehow to distinguish between classical and quantum regime of such kind of oscillator? And I really did ask it Sasha. When we were together, we collaborating, and we start to think about what kind of experiment can be done in order to really demonstrate this. But what is a somehow trivial answer and trivial explanation? So let us consider classical single 3-junction interferometer. Of course, it's somehow simplified. It's look like single junction interferometer, but nevertheless, if we apply magnetic flux, double degenerated state of such structure exists when you have apply magnetic flux of half a fluxon. But then if you slightly change magnetic flux, one minimum DCP, and we have jump of the flux from one minimum to other, and the same in other direction. So we have 2 jumps of the magnetic flux, or jumps of phase. And this is somehow classical regime when these states are separated. But when these states are not separated, we have also macroscopic quantum tunneling here. So in some words which you can really pronounce about such kind of structure, by the way, it's known classically as radio frequency squid, we have transition between hysteretic mode and non-hysteretic. Hysteretic mode here, because there is some kind of hysteresis, you have metastable state, which is not ground state, this is above ground state, and here you're always in ground state, if you have macroscopic quantum tunneling. And what we can see experimentally, you see, I show you. So if we have classical regime, and when we measure our impedance, because impedance is, it's important to note that we measure derivative of current flowing in the structure with respect to applied magnetic flux. So if we have such kind of jumps here, we see jumps in our energy here, because this is energy simply, minimal energy. So this is this energy of, and then when we go up, we're up, and then this jump is simply jump of here, and back is jump there. So we have such kind of structure. And what we will measure, if we measure as a derivative of the current, we will measure picture like that. And if we have quantum regime, we have anti-crossing here of the levels. Then if we change magnetic flux, we go adiabatically here, and we should measure something like this. So this is very narrow and big deep with small width. In first approximation, it is very clear. When we have classical regime, we have such kind of picture. If we have quantum regime, we have such kind of picture. But there is a but, and but is as follows. For quantum mechanics, this energy barrier should be really small in order to allow quantum tunneling. So if you have some uncontrolled noise or fluctuation, maybe instead of quantum tunneling, you have some kind of jump here. So by fluctuation, this hysteresis can be blew out, wash out simply. And I couldn't exclude it as experimentalist, because sometimes, you have some uncontrolled noise in your system and whatever. And I asked Sasha, okay, let us analyze such situation in more details. Even if we have fluctuation here, we have additional uncontrolled noise, what should I observe experimentally? Okay. But this is, I would like simply to show you experimental data. This is deep, which is quantum, And now I know that this is quantum because many years, it was a long time ago. And this is his theoretic picture, what I show you. And this is just experimental results which were obtained, which simply support this picture. So it's absolutely clear that it works. But this is somehow always when we neglect fluctuation. So let us analyze this little bit in more details. And this is unfortunately only one paper we wrote together with Sasha. It was 2009. We simply theoretically investigate magnetic flux noise in classical Moy type qubit, 3-junction qubit. How we did it? First of all, we wrote simply in an RSG model. We wrote, it's well-known RSG model for Josephson junction. And we have 3 junctions in our structure. So this is index I simply for different junctions. But in contrast to conventional RSG model, we have some kind of noise here. And this is somehow on white noise, is given by fluctuation and blah, 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 with this correlation and mean value of 0. So our aim was to solve this equation. And to be honest, for me, it was not so easy task. By how Sasha elegantly did it, it's really, I like it very much. And of course, detail can be found in this really modest paper, but nevertheless, first of all, after some algebra, he wrote some kind of Langevin equation, which really reflects the moving of the particle, random particle, in some kind of potential. And after that, such kind of equation, he did solve numerically. Yeah, but in order to be sure that numeric procedure is correct, he simply, for some particular cases, rewrites such kind of equation to Fokker-Planck equation. And then Fokker-Planck equation, he solved analytically. And after that, compare analytic results with numerical results. So it's really very elegant and easy way, and he did it somehow very fast. And yeah, it was really somehow surprising for me that so difficult, for me at least, difficult equation is solved elegantly and very easy. And after that, we come up with such kind of graphs. This is our experiment. We measure derivatives of current, which we write something like delta, and at different temperatures, classical deep has different width. And therefore, what it means? If we have classical case, we have classical 3-junction structure. In this case, we change a temperature and measure derivative of current with respect to flux. And we see that the height of the deep is changed, and width as well. And you see that parameter d here is simply normalized thermal energy, KT divided to Josephson energy. In contrast, in quantum case, when we change temperature, this just temperature divided to delta, also in energy, this is KT, of course. And in this case, only current is changed, so height of the deep is changed, but width is the same because temperature does not change the splitting of the qubit. In this case, we did experiment. This is experiment, by the way, we did together with Mira Greitzer. I saw he's also here, and I believe that Mira did this measurement directly, but Mira Greitzer is from Bratislava. He also was in those time collaborating with us, and he did visit us in Vienna as well, and Sasha was here, and Mira was, and this measurements is done Mira, and you see definitely, yes, that at the small change of temperature, you don't see that the width of the deep is changed, but only height of the change. Of course, at very high temperature, when you go to classical regime, of course, everything is like it is predicted. So I would like to conclude my short contribution with simply, so together with Sasha, we simply show that quantum and classical mold can be distinguished experimentally very easy by measuring temperature dependence of this deep, which is simply some kind of phase change across of resonator as a function of state of the qubit. Yeah, so let me finish my short contribution at this point. Thank you very much.
Thank you, Evgeny, very much. Thanks for the nice talk. Let us ask for the next talk, Pavel Sabo.
So
Yes, you please close.
how I close? Should I close it? I should close it somehow.
Please
Stop
allow
sharing.
me to share screen, please.
Yeah, stop sharing.
I will stop sharing.
Somewhere on the top of your screen, a red tab.
Stop it. Okay. Okay. Yes.
Hello,
Good.
Pavel.
Hello. Good. Can you see me? Can you
Both
see my
you
window?
and the presentation. Yes, but
Can you see the presentation?
not
Okay.
in the full. Yes. No.
No, it's
All
okay.
right. All right.
Good. Good afternoon. My name is Pavel Sabo. I'm working at the Center of Low Temperature Physics of the Slovak Academy of Sciences in Košice in Slovakia. First of all, I would like to thank the organizers to inviting the members of our group to this memorial seminar. You probably know that in our group, we have almost 40 years experiences with the point contact spectroscopy. And since the beginning up to today, we are collaborating with researchers from FTINT Kharkov. We started our collaboration just at the beginning with Professor Jansson, later with Jura Najdu, Kolja Bobrov, and also later we continue in this collaboration in Grenoble with Louis Janssen and Peter Wieder. And in our group, in Košice, we are running a homemade helium-free refrigerator and also a homemade helium-free refrigerator with STM system and also a point contact setup. And in this point contact setup, we are studying usually superconducting properties, applying point contact under reflection spectroscopy in unconventional superconductors like magnesium diboride, pnictides, or superconductors. And in this field, during last 20-30 years, we published more than 50 papers, and we have even more than 1,000 citations. Last few years, we started to collaborate with a group of Professor Varga from Šafarik University in Košice in the field of spin polarization studies in Heusler alloys, applying point contact spectroscopy. And that's why in my today's talk, I would like to speak about high spin polarization in cobalt iron tin Heusler nanowires studied by point contact under reflection spectroscopy. The results which I will present today have been published in this paper 2 years ago, or 1.5 years ago, in ACS Applied Nanomaterials. Okay, Heusler alloys, there are simply 3 compound alloys. As you can see, they can be defined with 2-1-1 or 1-1-1 structures. What is typical for them that the X and Y compounds are from the D block and the Z compounds from the P block of the periodic table. As you can see, this is really a very rich family. But what is important maybe from the view of our studies, that Heusler alloys reveal more stable 2L2-1 structure, which has the highest order, and from the view of spin polarization studies, systems with highest order are really required. As I said, this is really a very rich family of alloys. They can be metals with equal spins in the metallic state, or ferromagnets with very small spin polarization due to ferromagnetism, Also, then it can be, for example, semiconducting with a hard band gap. And also they can be like half metals, where we have two spin channels of the charge carriers, where the metallic channel is almost totally separated from with a band gap from the other one, in the case when we have 100% of spin polarization. It means this half metallicity depends on the size and the definition of this band gap. And if we have a system where spin polarization is smaller than 100%, in this case, we can predict that the band gap will overlap the Fermi energy. Here I'm just listing some basic magnetic properties of the Heusler alloys. Here you can see, for example, just in this column that they have very high Curie temperature, which is really very promising from the view of applications. And here in the last column, you just can see the spin polarization of these Heusler alloys. As you can see, the value of experimentally determined spin polarization is varying between 30 and approximately 90%. And what is interesting here also, as you can see that, for example, bulk samples reveal much smaller spin polarization, probably due to structural disorder, than thin films. And also here we can predict that if we will able to prepare micro or nanowires from these compounds, they reveal also much higher spin polarization than, for example, bulk samples. As I said, this is a rich family with enormous application potential. It means nanowires, Heusler alloys can be used, for example, for application like taking into account magnetocalorie effect, or they can be as a shape memory systems where spin polarization can be used, also thermoelectricity, etc. Really, the application potential of these Heusler alloys is huge. Now I will focus on the systems which, on the system of cobalt iron tin with the structure Al2-1. This system has been made with long thermal annealing at 1000 centigrades, and after that we used the rapid quenching method at the preparing of the sample. How did we prepare our nanowires? At the beginning we prepared just thin films, and after, if we found the right stoichiometry of our thin films, we continue at electrochemical etching of our samples. Here you can see just the schematical way how we prepared our samples. At the left, you can see this gray part. This is just a nanoporous alumina membrane, which has a net of holes or open tubes. The diameter of one hole is approximately 50 nanometers. And also the distance between these holes is in the range of 50 or 100 nanometers. It depends on the preparing method of these membranes. At the beginning, we just evaporated to the bottom side of this membrane thin film was gold. And this gold layer we used as a counter electrode for electrochemical deposition. And just during this deposition, we filled with all Heusler alloys this open tube. And after this deposition, just we took off with etching the aluminum membrane, and we obtained really a lot of nanowires. Here you can see such kind of halo of nanowires. And you know, if you have experiences with working with nanowires, it's not so easy to work with such a structure of nanowires. That's why we try to reduce the etching time, and we prepared some kind of arrays of nanowires, which you can see here at the right in this figure. This is a top view. You can see that really we have some protruding nanowires without alumina, and here at the bottom, just you can see that this is the bottom gold electrode. And we start to study spin polarization or physical properties of these nanowires in this array configuration. This is some schematic picture of our experimental situation. It means this is the net of, or the array of nanowires, and just we pressed our superconducting tip to the surface of this structure. Okay, but at the beginning, I think in this community everybody knows about what is point contact spectroscopy, but just to know, if we have a small point contact between the normal metal and superconductor, the charge transfer will be realized through Andreev reflection. It means the electron at the boundary is reflected as a whole, and at the superconducting side, we are inducing Cooper pairs. That's why, for example, in the point contact conductance at energies below the superconducting energy gap, we have seen this nice 2 times increase of the point contact conductance. But it is very important to notice that the Andreev reflection can take part only in the case if the electron has its opposite partner with the opposite spin. If we have, for example, a polarized system or a fully polarized system, the Andreev reflection cannot take a part. For example, here at the right, you can see a system where 100% of electrons is spin polarized. And if we compare, for example, this point contact conductance with the conductance at the left, you can see that at energies below the gap, we can see just strong reduction of the point contact conductance just due to the fact that the Andreev reflection cannot take part in polarized systems. And here is the situation, the real experimental situation. You know, it's in the reality, we have always some presence of surface barriers, and the surface barrier will create for us 2 symmetrically positioned peaks just at the superconducting energy gap, and it's quite strong barrier. We can see direct transition to the tunneling regime. But we know that this evolution of the point contact spectra can be described with the theoretical model of Blonder, Tinkham, and Klepp-Pike. But in the case, if we have, for example, at one side of our point contact a superconductor, and then on the other side a system with non-zero value of spin polarization, in this case, the point contact current will be defined as a weighted sum of polarized channel and of the Andreev reflection channel. And just the weight of the polarization channel, which is here defined with P, defines for us directly the value of spin polarization. Just we can say that we are determining spin polarization from Andreev reflection directly from the level of suppression of the Andreev excess current. Okay, here I just would like to show you how we perform, for example, this fitting procedure. Here you can see, for example, these red points. These red points are our experimental data, and this continuous red line is just our fitting results with 45% of spin polarization. And this red line is just a weighted sum of these blue points, which are representing 55% of the Andreev reflection contribution, and this green curve at the bottom is just 45% of the spin polarized channel. And this red one is just the superposition or the sum of these 2 curves. Okay, and now our experimental situation to determine spin polarization on our nanowire arrays. We use the superconducting tip of niobium with a well-known value of the superconducting energy gap, and just be pressed weakly to the surface of our nanowires, this superconducting tip. This is some kind of graphical or schematic presentation of our experimental situation. Okay, and now our experimental data. It means at the beginning, when we press just weakly the superconducting tip to the surface of these nanowires, we measured some point contact spectra. Typical point contact spectra are shown here in this figure. You can see the value of the spin polarization is changing between 30 and 53% just in these typical curves. But here I have more statistics. This is the most important result of this paper. This is just the dependence of determined polarization on the surface barrier or of the contact transparency. And here you can see just the point contact resistances. And what can you see? At the beginning, if we form the first point contact with the resistance of 35 ohm, transparency at about 0.5, you can see that if we reduce the point contact resistance, we can see nicely that the transparency, the point contact transparency is increasing, and we can see that the polarization is increasing approximately from 20 to 50%. It indicates to us that we have some oxide on the surface, oxide due to just this electrochemical etching of the alumina substrate. This indicates that we have a strong oxide on the surface of our nanowires. That's why we try to press a little bit deeper or point contact tip. And as you can see again, if we reduce, here you can see again in this range, typical point contact spectra. And as you can see, if we reduce the point contact resistance from this 25 ohm down to 10 ohms, again, we can see the same tendency. It means the transparency of the point contact is increasing, and also we can see nicely the increase of the polarization from 50% approximately to 70%. At lower point contact resistances, we were not able to measure because it was really difficult to obtain, for example, some spectroscopic range. But we are experimentalists. What did we do? It means we pressed so deeply the point contact tip to this structure, and just with horizontal movement of the point contact tip, we just break the nanowires. It means we made some natural cleavage of the surface, and we were able to obtain really freshly cleaved surfaces of our nanowires. And what can you see here? Again, the determined value of spin polarization, it means is at about 90 or 100%, extremely high. We have something like really half metals. And what is also interesting, what can you see here, that at point contact resistance is between 10 and 20 ohms. There is no this tendency that we are changing the point contact transparency together with the resistance. It means really this high spin polarization is the inherent property of the studied samples. Okay, just my conclusion. You can see that we were able, thanks to this special nanoarray configuration, we were able to obtain the extremely high spin polarization in our iron cobalt tin nanowires. And also, I think this method, just how to use nanowires to prepare point contact junctions, can be very useful for in the case of materials which have strongly destroyed or oxidized surfaces. Thank you very much.
Thank you very much, Pavel. And also Peter Samueli wants to take the microphone.
Yeah.
Please, Peter.
Thank you very much. So this was just a small example of how useful point contact spectroscopy can be. We spent really 40 years working together with people from Kharkov, mostly with experimentalists, as Pavel explained, but we were also privileged to meet this famous trio, Kulik, Omельянчук, Schechter, directly at the seminars of Kharkov. So we are really very happy that we can come to this your seminary. Of course, we are extremely deeply concerned by a terrible situation and attack on Ukraine. Not only just that we are friends with many of you, but at this corridor where we are sitting with Pavel, we have maybe 10 Ukrainian people sitting now with us. These are PhD students, these are collaborators who are already a permanent position here. And we are very much hoping that we can continue somehow this collaboration. So maybe I can really very shortly announce that our academy and our government is now within few days preparing a special scheme enabling to hire Ukrainian scientists any level from PhD students to professors giving him the possibility to come for longer, for maybe 3 to 4 years. So I already let some information to Juran, but if you are interested, I can also hand it to you. Thank you so much, and we feel very much with you. Thank you.
Thank you so much, Peter and Pavel,
Thank you.
for the warm words, for the proposition of versatile help. Thanks. Now, if Professor Tafuri here, I saw you're there, Francesco. Are you? Can you join? Colleagues, we were originally thinking about making the break, but now we think that we'd better continue without the break. So we have, I must announce, 4 talks left: Francesco Tafuri, Professor Naiduk, Professor Bondarenko, and myself. So now probably it would be logical after the talks which we now had to ask Professor Naiduk, Yuri Georgievich, please, our director of our institute, and the friend of Professor Омельянчук.
Okay. Can you see my screen?
Not yet. Now yes. Now yes, but without
Yes.
presentation.
Okay,
We do see your screen, but not the presentation.
I see my presentation. What I have to do? Share screen. You cannot start screen. Share while the other participant is sharing.
We do
Somebody
see
is sharing.
your screen, but not the presentation. Can you open your presentation?
It seems to me, sorry. It seems to me we see now the screen of Sabo. You have to stop sharing.
Maybe. Pavel, please stop sharing. Or I can do this.
Nice.
Thanks.
Okay, can you see my screen? Once again. Can you see my screen?
Almost. Yes,
Okay.
now yes.
Thank you, Chairman, for this possibility. So I would like to tell you about contribution of Sasha Омельянчук to this area of point contact spectroscopy. It will be a little bit short historical overview. So I met Sasha about 46 years ago when I started to work in Department of Point Contact Spectroscopy headed by Professor Jansson. In that time, main scientific work in department was moved from tunneling spectroscopy to the point contact spectroscopy method. Because 2 years before, Professor Jansson published his famous paper. Just a moment. Okay. Professor Jansson 2 years ago published his famous paper, which is maybe paper which started this method of point contact spectroscopy. Namely, he studied small metallic point contact between two metallic films separated by thin oxide. He measured nonlinear IV characteristic and observed that second derivative of IV characteristic is looks like a spectrum, and namely spectrum of phonon spectrum of, for example, in this case of lead. When he compared this spectrum with known spectrum of electron-photon interaction, which is shown here, it is electron-phonon interaction spectra measured by tunneling spectroscopy, and this solid line is point contact spectra, a second derivative of IV characteristic of small point contact. From this similarity, he concluded that indeed this method of measuring nonlinearities of point contact can use it to receive spectrum of electron-photon interaction. He proposed some phenomenological theory, but it's still strong theory was needed at that time. And in 1977, a group of Professor Kulik with Sasha Омельянчук and Robert Schechter published a series of papers which explain that indeed measurement of nonlinear characteristic of small point contacts can be used to study electron-phonon interaction in metals. The first paper was published in Jet Letters in March 1977. In this paper, Sasha Омельянчук was the first author, as you see, and in this paper, rigorous solution was presented as the problem of electrical conductivity of normal contacts. You see expression for the second derivative, and this second derivative indeed includes this well-known electron-phonon interaction function of Eliasberg, electron-phonon interaction function. Next papers they prepared and sent in 4 days to the solid-state communication. It's the title of electron-phonon coupling and phonon generation in normal metal microbridges. Here you see that they shown that in case of point contact, electron-phonon Fermi distribution function is split in two parts, and difference between energy between these two parts is equal to the applied voltage times electronic charge. It means that the point contact in this case looks like accelerator of electrons. So electrons in point contact, in the case of if size of point contact is much less than electronic mean free path, elastic and inelastic, in adjusted electron have excess energy sharply equal to the IV, and in this case they can scatter in the point contact, and by different quasi-particle excitation, in most cases it's phonon, because phonons are present in all solid state. So they also calculated in this case of electron-phonon interaction how it looks second derivative of IV characteristic, and you see here this equation with electron-phonon point contact electron-phonon interaction function J, and here is a comparison of two expressions for the Eliasberg function for electron-phonon interaction and point contact interaction function. You see that the difference is only in this part where velocities of electrons which take part in the conductivity is these velocities are added. So in a few months they published the most full paper in the Journal of Low Temperature Physics, Electrical with title Electrical Conductivity of Point Microcontacts and Spectroscopy of Phonons and Impurities in Normal Metals, where all aspects of theory was presented. So here is distribution function in the middle of the point contact and on both sides of the point contact. And this geometrical form factor, which appears additionally in the Eliashberg function, it's gives this K factor results in situation when in the case of point contact only scattering on large angles are most important. It means that if, for example, z components is equal to 0, it means that electron trajectories is along partition between two metals. Of course, this trajectories give no contribution to the point contact spectra, and the main contribution goes from the electron which scattered by angle pi. So for this investigation, experimental and theoretical investigation, which established point contact spectroscopy method, in 10 years, Janssen, Kulik, Омельянчук, Schechter received diploma on discovery. It was in former Soviet Union very important diploma. So I would like also to show you another paper by Sasha Омельянчук. Of course, it's logically to expect that not only electron-phonon interaction, but also different interaction of electrons with different quasi-particle excitation, which led to the scattering, can be studied by point contact spectroscopy method. And here is example of study electrical conductivity point contact with magnetic impurities, or so-called Konde effect in point contacts. Омельянчук and his colleague Igor Tuluzov developed a theory of Kondo scattering in the case of point contact, and they have shown that in this case additional feature in the point contact spectra appears, which is connected with scattering and magnetic impurities. Here is expression for the second derivative at a different condition, and here is this figure shows how this second derivative must look like in the case of Kondo scattering. So sign of second derivative depends on the exchange integral, and using such methods, it's possible to, using point contact, possible to, for example, to find exchange integral from point contact spectra and sign, of course, sign of this exchange integral. The theory was of Омельянчук and Tuluzov in the case of Kondo scattering was proven by experimental experimental results. Here is shown point contact spectra of copper with small amount of manganese, and you see that addition to the phonon spectra contain this zero bias anomaly, which looks like theoretical calculation, and this experimental results confirm also theory developed by Sasha Омельянчук and Igor Toulouse. And last example, but not least, here is a paper where Sasha Омельянчук studied nonlinear effect in point contact between superconductors. And in case of superconductors, they show that in general electron-phonon interaction spectra are also present in the point contact spectra, but additional feature appears, which is connected with renormalization of electron-phonon interaction, renormalization of density of state due to electron-phonon interaction, as it is usually characteristic for tunneling point contact. Also, they found that here is shown this correction to the point contact spectra, which have additional feature in the first derivative. And second, they found also correction to the point contact spectra, which reflects elastic scattering of electrons by non-equilibrium phonons generated by electron flow. And this feature appears with phonon in the vicinity of one whole points in the phonon spectrum. So finally, I say that Sasha Омельянчук made a decisive contribution to the theory of point contact spectroscopy in the development for investigation of quasi-particle excitation in solids. Of course, this paper will keep memory of about Sasha Омельянчук for a long period, and they will also give us hope that we will continue this investigation for a long time. Okay, so thank you very much for attention.
Thank you, Yuri Georgievich. Now I would like to invite Professor Tafuri, please. Yuri Georgievich, please stop sharing. Yes, Francesco, we can see you.
Thank you. Hello, Sergey. Hello to everybody. Okay, just a second. Okay, I'm here to share the.
We can see your screen.
Okay, good. Just.
And the presentation.
Okay.
And
can
now,
you see?
All right. Yes.
Okay. Okay. Good. So I will give, following Sergey directions, also a few memories. I thought that, closer colleagues could give a better presentation of this scientific stature, and so I limit myself to a few memories to honor really a nice gentleman and a great scientist. And so, a way to do that is probably most of you know this picture, that it was the conference in Kharkiv in 1991. And here is a lot of you, I guess, are here. And there is Sasha, and it was also my very first international conference, in Europe. And I start from that again for a memory of a great scientist and of a great school, and also I remember Sasha here in Napoli, and I will tell you a story in a moment. So just to start, this was a very important step also in my career, to start with so many great colleagues and scientists. And these are again two pictures of the same week. This was taken in Kharkiv, in downtown, and this was probably a social dinner. And this is another conference that followed the one in Kharkiv. It was in Nijmegen 4 years later. Again, here is Sasha, and is a little bit of enlargement. And as has been described up to now, Sasha has given with the Kulik sector, gave contributions to hold the theory. But I would like to to extend, for the Johnson part, Kulik, Omельянчука theory 1 and 2. These are from Likaret review, and has been an amazing contribution also to understand the behavior of Johnson junctions in all different conditions. And this, this is the Antonio Barone book, and there is a lot of this great physics everywhere. And again, stressing the importance of the connection with our school of Antonio Barone, with the school in Russia, Ukraine, in Kharkov, with Kulik, Омельянчука, Janssen. I remember Kulik for long periods here, and also Sasha here with us. This is a picture, one of the few that I found, Antonio Barone with Abrikosov and Andreev. This was probably in 2003. And probably all of you know that Antonio was very attached to your culture, and this passed to all of us. And we are all very in depth with you, and we feel a lot of scientific closeness with the whole culture. I've seen first also before Peter, a vortex, a big community that continues to give important contributions. And these are a few examples, and also want to recall this very nice volume that was where Sasha invited me to write a contribution. This was a few years ago, just to tell that apart from scientific contributions, I think it was a leader and was able to keep a lot of ideas. And also later I remember, I have memory of the collaboration with Zhenya Ilishov, with Alex Zagoskin. We never met in Vancouver together, but we were at the time of the wave. But I think that contributions were really wide and went also to what ideas are still present in what is we call quantum technologies. And I want to conclude this really brief memory and to honor Sasha. Also keeping this is our new campus in Napoli that extended this. We are a large group, and what I want to say is that he's still the results of this research are important to us and to what we do here. and also with quantum technology. And I would stop here and leave the word to those colleagues who are closer to him. And my only point is that, and this is not only to me, but the whole school of Antonio Barone, how we feel close to Sasha, and how we feel close to this not nice situation that is currently not. And so my presence is also for this. So hello to everybody. Ciao, Sasha. We miss you, and for sure we'll take profit of all your research and what you have generated. Thanks to all of you.
Thank you very much, Francesco, for very moving and warm talk. Thanks a lot. Now all of you can see how geography of our seminar is wide, both in terms of science and in terms of from where the speakers are. I must say is that I'm the head of the department after Professor Омельянчук for some 5.5 years, and also Alexander Nikolaevich was the head of this department for some 16 years, and I would like to give the microphone to Stanislav Ivanovich Bondarenko next, who helps now me to be the head of the department, and who used to help all the 16 years to Alexander Nikolaevich in this difficult task. Stanislav Ivanovich, are you there?
Unfortunately, I have not now English version of my talk. I can speak by Russian only. Maybe without my talk, or I can try to say by English very short.
As you wish, but I have another idea. We can exchange the place of talks. Now I can deliver my talk in English, and then you in Russian, and without any hurry. So if you do not mind, and then those who do not understand Russian can spend time to other things. Don't you mind, Stanislav, if we change the places, if now I give my talk?
Okay.
Okay?
Okay.
Mm-hmm. Yes. Now, can you see my presentation in the full screen mode?
Yes.
Uh-huh.
Not full screen yet, Sandy.
Not the full screen. Uh-huh. And I'll restart it. Just a second. Can you hear the noise from outside? The shelling? Yes, that's now how we live here in Kharkov. Let me try to concentrate on my talk. Can you see it in the full screen mode?
Yes.
Mm-hmm. So I would like to tell about my scientific work together with Alexander Nikolaevich of course, mostly in Kharkov, and also visiting Jena and Waco for 2 decades. Firstly, I'd like to show you the diagram several people mentioned today. All those publications. How many publications Alexander Nikolaevich had with different people. And interestingly, I didn't find any single paper of Alexander Nikolaevich without co-authors. So much he liked communications, so much he didn't separate science and friendship and communication. Well, my first probably work with Alexander Nikolaevich was on point contacts of 2 superconductors with the tangential supercurrent, with the current along the boundary between 2 superconductors. This model you have seen, and what was interesting and important related to the D-wave contacts Professor Zagoskin mentioned, and the idea was to control the states of Josephson junctions between D-wave superconductors with tangential current. So we studied these both in conventional and unconventional superconductors. Then, we, similarly to D-Wave Corporation, we changed our attention from unconventional superconductors to conventional ones, which operate in quantum regime. So we studied dynamics of superconductors, of superconducting structures of qubits, both Rabi oscillations in resonant regime and Landau-Zener transitions in adiabatic non-resonant limit. And this particular paper was devoted to numerical solution of Bloch equations and finding the crossover between these 2 well-known regimes, but usually considered in different contexts. And in particular, we studied multi-photon excitations. When to excite qubits, we need several photons. Here's the next work with Jena group, with colleagues from Jena, on multi-photon transitions in such superconducting qubits. Here, Cooper pair box, and in these and in several subsequent papers, we described the experiment, often with a nice agreement between the experiment and the theory. In particular, here we described the qubit in terms of what is sometimes called quantum inductance. So that, interestingly, the probability was not only the observed value phase shift was not only proportional to the probability, but also to the derivative of the probability. An unusual feature, but this helped to explain these and several other experiments. What Professor Ilyichev told us about finding boundaries between classical and quantum behavior. And this is the paper, one out of the series where with Professor Омельянчука we studied this. And here are the pictures which Gregor have shown you. Gregor has shown you how we related our theory to the experiment with Yakov Semyonovich Greenberg, who is also here today. And the textbook, which we also mentioned, Quantum Coherent Phenomena in Josephson Qubits. This monograph was in Russian, Омельянчук, Ilyichev, and myself. And my short presentation of several our selected papers, I would like to finish with the picture having the sakura blossom in Waco in the group of Franco Nori and several people you can see whom you know, and Alexander Nikolaevich in the environment of international colleagues. Probably with this, I would like to finish my talk, and I'd like to thank those of you who contributed, and maybe now we'll have the presentation from Stanislav Ivanovich Bondarenko, and maybe somebody else wanted to add something. If there are no questions or comments, then please, Stanislav Ivanovich. The next and the last talk of our seminar.
Sergey Nikolaevich, please, can you formulate your position in the war, Russian war against Ukraine?
Let me interrupt you, Sergey. The subject of our seminar is different.
Sergey, please.
Let me ask Stanislav Ivanovich if he's not disconnected. You're here. Да, пожалуйста, Станислав Иванович.
Окей. Я буду говорить о некоторых событиях в жизни Александра Николаевича. И мой доклад посвящен его 75-летию и 50-летию его работы в физико-техническом институте низких температур. Так, меня не слышно?
Слышно? We can hear you.
Так, translate, please. Or not?
Ну, давайте на русском языке, Станислав Иванович.
На русском? Хорошо.
Вам же ж так легче, верно?
Да. С 1964 по 1969 год Александр Николаевич являлся студентом физического факультета Харьковского государственного университета. И в этот годы он особенно сблизился с известным теоретиком Моисеем Исааковичем Кагановым, с которым он и сделал свою первую научную работу. Она была посвящена некоторым квантовым состояниям металлов. С 1970 по 1971 год Александр Николаевич служил в Советской армии, в Германской Демократической Республике и получил звание капитана противовоздушной обороны. С 1972 года Александр Николаевич сотрудник физико-технического института низких температур, где начал работать в отделе известного физика Игоря Ресловича Кулика, позже академика. В этой среде работали такие известные физики-теоретики, занимавшиеся проблемами сверхпроводимости, как Владимир Галайко, Анатолий Свидзинский и некоторые другие. Это, безусловно, повлияло на кругозор Александра Николаевича в области сверхпроводимости и проблем сверхпроводимости, что способствовало в дальнейшем его быстрым успехам в этой области. В 1975 году состоялась наша совместная с ним командировка в Германскую Демократическую Республику, город Йена, в университет имени Шиллера. Эта поездка была посвящена теоретическим работам и экспериментальным работам в области сверхпроводящих квантовых магнитометров, которыми в это время занимались ученые как университета имени Шиллера и также ученые физико-технического института низких температур. Поездка была весьма примечательна. Она включала посещение Дрезденской галереи, Ваймара, музеев Гёте и Шиллера. Вскоре появилась широко цитируемая работа Омельянчука Кулика по теории сверхпроводящего металлического микроконтакта, обладающего джозефсоновскими свойствами. С этого момента имя Александра Николаевича стало широко известно мировой общественности. С 1999 года Александр Николаевич заведующим отделом номер 16 физико-технического института низких температур. Именно он дал отделу номер 16 новое название «Отдел сверхпроводящих и мезоскопических структур». Мое сотрудничество с Александром Николаевичем стало наиболее тесным, когда я исполнял обязанности его заместителя с 1999 по 2018 год. За это время я достаточно близко узнал его не только как ученого, но и как человека, который всегда относился к работам своих сотрудников с большим вниманием и заботой. В частности, благодаря его поддержке была проведена успешная работа по изучению свойств новой квантовой структуры в виде квантового интерферометра постоянного тока, шунтированного сверхпроводящей индуктивностью. Эта работа показала возможность одновременного измерения энергетической щели сверхпроводников и времени релаксации сверхпроводимости фактически в одном эксперименте. Александр Николаевич выступил в начале 2016 и 2015 года с предложением о сотрудничестве с учеными Китая. Благодаря этому предложению мы установили тесные связи с Чунцинской академией наук и технологий и в течение 5 лет выполнили с китайскими учеными одну из пионерских работ в области внедрения сверхпроводимости в практику. Эта разработка касалась создания первого в Китае сверхпроводящего магнитного сепаратора. Причем сепаратор был создан на базе высокотемпературных сверхпроводников. Нельзя не отметить замечательные встречи Александра Николаевича с Владимиром Михайловичем Свистуновым. Володя Свистунов – это один из тех известных широко сейчас ученых, которыми первыми наблюдали нестационарный эффект Джозефсона. Этих трех ученых мы хорошо знаем. Это Игорь Янсон, Игорь Дмитренко и Володя Свистунов. Во время командировок, которые Александр Николаевич имел в этот период, в особенности много командировок в Японию, он мне преподнес вот такой сувенир самурая, который стоит всегда передо мной и напоминает мне о прошедших годах и дружбе с Александром Николаевичем. У меня нет совместных научных публикаций с Александром Николаевичем, поскольку я экспериментатор, а он теоретик. Хотя бывает и такое, что такие совместные работы появляются. Но у нас, к сожалению, не было. Совместной работой, заметной для меня во всяком случае, была работа над юбилейным номером журнала «Физика низких температур», посвященная 90-летию известного физика Игоря Михайловича Дмитренко, основателя отдела номер 16, в котором я проработал вот уже более 50 лет. Нельзя не сказать несколько слов о семинарах, которые проводил в отделе Александр Николаевич. Это были замечательные события для всех сотрудников нашего отдела. Александр Николаевич умел очень ясно представить физическую суть любых явлений, которые докладывались на этих семинарах. После его разъяснений многое становилось ясным и понятным. Александр Николаевич не только ученый, но, можно сказать, он и гуманитарий, поскольку все в нашем отделе и за его пределами знают о его таланте в области стихосложения. Его стихотворения, которые он сообщал нам во время встреч, надолго останутся в нашей памяти как пример очень глубокого понимания жизни. Все эти стихотворения были наполнены глубоким философским смыслом. Я думаю, если бы он не стал физиком-теоретиком, он бы стал выдающимся поэтом. Александр Николаевич, что и видно из тех работ, которые доложены вот на этой нашей встрече, был одним из основателей работ, вообще изучения квантового мира. Он жил с этим квантовым миром и очень часто возвращался к той мысли, что в науке сейчас нет ничего более важного, во всяком случае в физической науке, чем изучение квантовых явлений, которые сейчас, как мы видим, находят все большее понимание и распространение в обществе. Ну, одним из свидетельств его деятельности в этой области явилась здесь показанная всем монография, а точнее труд совместный Александра Николаевича, Евгения Васильевича и Сергея Николаевича. Мы всегда помним и будем помнить Александра Николаевича как выдающегося человека, как выдающегося ученого. Такие люди рождаются, по-видимому, очень редко. Будем думать, что квантовый мир, которым он был увлечен, и сегодня связывает нас с ним и будет связывать впредь. Спасибо за внимание.
Thank you so much, Станислав Иванович. Большое спасибо.
Ну вот, кто-то понял, кто-то нет.
Very
Я-
nice memories. We have colleagues who can translate and who can tell to our friends who do not understand Russian that the main facts from biography of Alexander Nikolaevich. And in particular, what you said about the warm and important attention of Alexander Nikolaevich to the seminars. We do continue this tradition, and now we have the seminar. So we commemorate him, Professor Омельянчук, with the seminar. And I'm very grateful to all the speakers, to all of you for participating in this seminar. I hope that this disaster, the war, which we have here in Kharkov, will end up very, very soon. Alexander Nikolaevich died virtually a few days before this disaster. He couldn't even imagine that things like this could happen. Something unbelievable, surrealistic. I hope that this will end up soon. We'll return to our peaceful and normal life. We'll continue meet each other, and we'll continue discussing the works, the ones related to Alexander Nikolaevich previous works. We'll continue. We'll discuss. We'll hopefully sit around the table and tell each other warm words and remember him. I'm very grateful to all of you for participating. And if you do not mind, I'll finish this seminar. Yes,
Thank you very much.
All our guests, you are invited to our weekly seminars. Hopefully, this will continue. Of course, we have the pause now in the seminars, but hopefully we'll continue. And all of you are welcome to take part, both as listeners and speakers. We'll be helpful to see you. Thank you.
Thank you. Bye.
Thank you.
Thank you.
Thank you, Sergey. I would like to add a few words. Today is 30 days after death of Sasha Омельянчук, and it is symbolic that just now we have 40 days after death, and now we have 40 participants in the seminar.
Nice observation.
And thank you, Sergey, for organizing this very important and moving event. Wish you all the best.
Thank you very much for supporting this.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Слава Україні!
Bye-bye.
Слава Україні!
Slava Ukraini.
Героям слава!
Thank you, Sergey. Keep in touch.
Yes. Bye-bye. Bye-bye. До свидания.
Bye. До свидания.